Hello student, so welcome to Combustion tutorial 1A. Today I would like to show you how we do mass balance for combustion when we have theoretical air or excess air given in the question. Okay, so the questions, so we are going to use this example where butane is burnt with oxygen producing carbon dioxide and also water. So this is the equation. Okay, the question wants us to find the molar composition of the product stream if conversion of butane is 100% and the theoretical air is supplied. So we will use 100% of butane that is fed into the process. So if since theoretical air is given, that means it will follow the conversion. So 100% of butane will be used, theoretical air, oxygen, all will be used because it's theoretical, and producing carbon dioxide and also water according to stoichiometric because it's theoretical. Okay. So the feed given or basis of our question is 100 mole. So let's plot this question into process flow diagram. So we know in reaction is here will be furnace because it's combustion. So for combustion then we'll use the unit operation here furnace, where for our feed there will be butane 100 mole. But we do not know number of mole of oxygen and number of mole of nitrogen that comes in the theoretical air, because we also do not know how much is theoretical air yet because we haven't calculated it yet. Okay, so the question wants us to find the molar composition of the product stream. So since butane is 100% used and we are being supplied by theoretical air, which will follow how much butane is fed. So we know that we only will have CO2 and H2O as our product. We do not have any leftover of butane here and also oxygen. But since N2 is not being used for the process, N2 that comes in will equal to N2 N2 that goes into the process will equal to the N2 that goes out from the process, because N2 is an inert to the process. Okay, the question wants us to find the molar composition of the product stream. Given basis of one of your given information of one of feed is 100 mole, which is C4H10, and the air that goes into the process is theoretical air, which follows requirement of 100 mole butane here. Okay, therefore, in order to find this, we need to find this first. Okay. Okay, let's see. How much is actually O2 that goes into the process, because once we know O2 then we can calculate how much of CO2, H2O being produced. Okay, and O2 theoretical, to find it we need to follow, since it's theoretical, so we use 100% of butane, right? So 100 mole butane times with the relationship between O2 and also butane in this equation. So we obtain oxygen theoretically that goes into the process is 650 mole of O2, which equivalent to also NO2I here. So what O2 that goes in is 650 mole. Okay, now how much is, in order to find N2, we need to find how much of air, theoretical air that goes into the process. Okay, since we already have theoretical O2, we can find theoretical air. We use this equation where 0.21 times by N air theoretical equals to NO2 theoretical. In previous part 14, we have looked into that equation. So now we just rearrange the equation. So we want to find N air theoretical is equivalent to NO2 theoretical, which we obtained just now, divided by 0.21, because the percent of O2 in oxygen is only 21%. So we already have this 650 mole of O2 theoretically. Divide by this, we'll get the total mole of air theoretical that goes into the process is 3095.24 mole of air. So from here, we can find N2. We know this much of mole air, and since N2 is 79% from air, so we use this equation 0.79 mole N2 times by total mole of air, then we get mole of N2 that goes into the process theoretically. Okay. And nitrogen that goes into the process is equal to the nitrogen that comes out from the process, because nitrogen is inert, therefore in equals to out equals to 2445.24 mole of N. To find CO2, H2O, we use this since this is our reactant, our butane, and it 100%, it reacts, it converts 100%. So we use this reactant, 100 mole of butane, times by the relationship of butane with CO2 in the equation. So we'll get the amount of CO2 being produced, 400 mole CO2, because 100% conversion of butane. For water, so we use 100 mole of butane times with the relationship stoichiometric ratio of butane, water with butane, then we obtain 500 mole of H2O. To find the molar composition of the product stream, so we have to find first the total mole of the product stream. So we have to add all the mole of product stream. Okay, so we obtain 3,345.24 mole. That is the total mole of the product stream. To find the composition, so we use the fraction, how we calculate fraction. So 400 mole of CO2 divided by the total mole. So we obtain the composition for CO2 equivalent to 0.120 mole CO2 per mole. So don't forget your unit. So now we leave it in terms of fraction, molar fraction. So for water, so we use the same method. So we obtain this is 0.150 mole water per mole. And for nitrogen, 0.73 mole of nitrogen per mole. So if the question wants you to convert it into percentage, just times 100 with the molar fraction. So you'll get it, the molar composition in percentage.